Yeah, in the last class we discussed about primary structures. Again, we discussed the same primary structures that we have seen. Yeah. Yes. Stratification and particularly we see these are structures in sedimentary structures. One it is a stratification or bedding. Second one it is a graded bedding. Third one it is a cross bedding. Fourth one pebble imbrication. Fifth one is making of bedding planes, and fifth one is a mud flats. These structures we can see in we see these structures in particularly in sedimentary formation, and also we have some other formations of other structures in igneous formations. Those it depend on their flow and of formations, and other structures what we have seen in lava. Second one is columnar joints in a lava formation. Again, flow structures in a plutonic class. These, when you come into the sedimentary structures, it is a stratification and bedding. The stratification means actually the layers will be formed layer by layer. The rocks will be formed as per layer, and these beds maybe it's varied from massive layers to delicate and those are having the small lamina part. They are separated from each other by bedding planes, so that stratification arises from variations in one or more physical or chemical characteristics of sediment, in which the which are occurs into the vertical to the bedding, and some of the factors which are causes of stratifications are between the different layers. One, it is depend on chemical composition. Second is color. Third one, it is the grain side. Fourth one is the degree of sorting. Fifth one, it is the degree and type of packing. Sixth one is the coaction. Seventh one is cementation. Eighth one is permeability and porosity. And it has a resistance to erosion. Those are naturally the stratification we can see indirectly from a sedimentation as different formations. The layers which you can see in deep sea carbonate, and silicious both and other layers to generally see. In stratification, maybe it is produced indirectly when the water it is agitated. Then the sediment is reworked, and the sediment deposited previously maybe it's broken up, and again it is going to be redeposited. It is occurs the most commonly in shallow water. Some bedding may be produced under the combined condition of direct or indirect stratification. That means here it's when the layer by layer which they are going to form, some pressure will be working. Some pressure will be working. So automatically we may find out the different fractures and some other broken points in the same formation. Second one is a graded bedding. Yes, second one it is a graded bedding. When the sediments are set as a graded, that means here those will be formed according to the grade formation. The graded sediments which are showing gradually decreases in the size when we see the from bottom to the top of the layer. It is producing Due to the settling of a substandard material and other materials, they are formed very rapidly and flowing in sediment and laden current when it is experienced, then suddenly decrease of the velocity of the flow. So here we will be working the turbidity also to play an important role in the one. And then normally it is showing as a graded bedding. In the A picture, it's a normally it's showing as a horizontal beds. Uh, each bed, each bed, it's getting thinner towards the top. And the second one, it is a dipping beds. Dipping beds right to the side up. And third one, it is a C vertical beds towards the right. And D, it's a turned over and completely these will be turned. So then cross bedding. If you see this is a cross bedding, the lamination orientation it will go, the angle is going to be changes when it is going to be formed as a bed. The upper and the lower will be changed, and the most diagnostic form, the cross bedding to be having the cross laminations tangential to the lower extremities. In the most diagnostic form, the cross beds are the cross laminations, which are tangential to the lower bedding surface, and those are the very sharply truncated along the upper surface. Cross bedding it is inclined in the general direction the sediment transportation according to the current flow. Sometimes maybe these beds are having a top edge and the cross-bedded strata in some cases. However, it is intersecting to the previous beds, and mostly we see in deltas with the lower beds and the quite abrupt. So it leads to formation of the cross-bedding. Yeah, pebble imbrications. In a pebble imbrication, it is characterized by the overlapping of disc-shaped rock pebbles, which lay the beds of streams or on streamy stony beaches. In particular, the stream pebbles lean downstream and beaches away from the water's edges, and thus mm, thus it becomes a very valuable interpreting to current direction and direction source for it's source for conglomerates. So these type of current bedding it's called torrential cross bedding, and it is supposed to as a under the conditions of very rapid sedimentation. And marking on bedding planes. The marking on bedding planes maybe it's both inorganic and organic origin. The inorganic markings include the ripple marks, the channels, the rain sole markings, load casts, and the organic making included the or tracks in the tails, burrows, and etc. and etc. The ripple marks are repeated waves, forms seen in sand and silt and mud also. These may be produced in shallow water due to the action of the current waves and other play. It's a playing wind. It's a playing a very important role when it's bringing to the surface of the water, and when it is moving to the surface on the wind, it is an action. It will take the action on the surface of the head, so that we may get sometimes oscillation of the ripple mark and the overturn of cross oscillations and original current ripple marks and overturn the last current ripple marks also will get it. Actually, we see the two types of ripple marks we can see. One it is the oscillation ripple marks, and it has a symmetrical concave form, and it consists of the broad troughs and their convex downwards and sharp crests that we may point out at upward. These are formed in bodies of standing water. The current ripple mark or the other hand in the symmetrical we see around the every farms. And during the accumulation of the sediments, particularly by a river action, erosion may be an alternative with deposition. After the deposition of the sediment, channels may occur the swiftly showing the streams during the flood time. So at the time we'll get the contains bedding with the original sediment. Yeah, sometimes we may get the raindrop impressions. Sometimes we may get the sole single marks and liquefaction formations. When the sandy deposit or sandy mud, if it is available at the time, we will get the raindrop and the sole marks also. And some organic marking also we may find out it's produced by the excision of animals, and we may find out the same in shallow water and mud flats. These are mud flats you may find out on the river bottom, lake beds, or the beach dries out. It will characteristically become broken into the polygonal blocks that are bounded by the mud flats or sun cracks. These cracks result due to the evaporation of the water and the drying and the consequent shrinkage. Mud cracks, when filled with sand, maybe it is a preserved. Those found in the ancient sediments which are used to interpret the depositional environment. So then when you come into the igneous structures, the igneous structures primarily which are formed by the solidification of the primary magma. And the flow and the other structures in lavas also that we will find out. The primary structural characteristics of volcanic rocks are largely dependent on the flow of the lava, which in turns controlled by the viscosity of the lava and physical environment next to it. The chemical composition is great influence on viscosity, although temperature and gas sensor also temperature. It's also playing the very important role, and these are all the very important factors. Suppose if we see the mafic and basaltic magma, which are having a very low viscosity and are very low fluid, whereas the calcic or rhyolitic magmas possess uh, highly viscosity and thus tends to be very stiff. Then, if we wanted to see the differentiation between the fluid setting of basalt and the rhyolitic magmas, partly which are accounts for the dominantly exterior habits of basalt and the dominantly intrusive basalt in habit of granites. So the physical environment sometimes maybe it is getting to the eruption, and it also has been influenced on the surface when it's the lava it's coming to the surface and also flows on a surface. And one more structure is columnar jointing. In a columnar jointing, the columns which are very characteristic of some we see in a basalt flow movement, which are produced by the particular columnar joint and fractures also. The columns tends to be a polygonal because of the fracturing is a polygonal as in this case for mud cracks. The orientation of each column it may sometimes reveal that the direction of a lava flow and column may locally plunge towards the rear of the flow. Some flow structures also we can see in plutonic rocks. In a plutonic bodies, the flow structures uh, form a relatively early process, which are replacement of the magma, and they continue to form until the mass become very rigid. The Yeah. The flow characteristics of a proton, which are reflected on often in the alignment of the crystals. The most commonly occurring crystals, which are useful in the study of alignment patterns, which are made like the crystals formed as in the form of hornblends. Tubular crystals of feldspars are also we see in platy as a platy uh, uh, peaks. And elongate minerals like hornblends, feldspars, we see along the alignment when it's producing with lineation. The mineral lineation is commonly oriented travel to the local flow direction. It's a tabular and the platy minerals when aligned they produce flow foliations. In particular, we see into the igneous bodies. Foliations in igneous rocks are typically produced by the arrangement of mica and which are parallel to the broad 010 phase we see in feldspars. When its foliation is reflects the laminar flow of the introducing the magma. So these are the structures. One, it is lineation formation, and second one is the foliations. Some alignments which have sometimes a xenolith and the inclusions, and actually it is related to the primary internal structure within the protonic bodies. Yeah, what is the importance of the primary structures? Yeah, it's useful as a guide to the formation and evolution of primary structures, the sedimentary structures in a particular area, which are useful in many ways. They are useful in the interpretation of structures for the formula areas. It is only through a proper understanding of primary shape and attitude of a strata that we are able to receive that information and measurement amount deformation. For example, if there is word move on a bedding in sedimentary rocks, there would be far less evidence of deformation in deformed rocks. So that's in deformation of the rocks, there may be a abundance of microstructural events which it is indicating which it indicates that the deformation, but because the shape of various units before deformation is it's not known, it is generally too difficult to interpret or predict the structure of the conflicts. But interpretation of deformed bedded sequence can be done with more confidence because it is assumed that the bedding where it is initially or it's a where it is a less in the plan. And particularly these primary structures provide considerable information on the tectonic environment. In this, the study for deformed rocks is ultimately aimed to understand the total history of the deformation of a rock and not just the deformation of the history. And furthermore, the process of deformational of a deformation may not necessarily be isolated in time. For example, the history of a mountain chain may show an intermingling, the process of deposition and deformation in such a way type of sediment deposited being deposited can often provide clues in the outstanding tectonics. So these are the uh, useful uses from the primary structures. And yeah, go into detailed study of structures. Importance of structures, we see the actually this block which is consisting of uniformity, unconformity and joints, folds, faults. We are now coming to the unconformity. Yeah, actually, the important for primary structures, which are to be we can study the structural theory. They are related to the unconformities, joints, folds, and faults. Nonconformity joints are discussed in this unit. Two features will be discussed. And nonconformities are the blocks of stratigraphic sequence or subspaces or non-deposition or surface, maybe it is erosion. And the joints are a smooth to surface found in the rocks. These two types of structures are very important structures in geology, and it is useful to identification of the mineral resources and also to plan engineering constructions also. Non-conformities. During the process, the deposition, sedimentary layers, and the volcanic layers, which are please. Yeah, during the process of a deposition, actually the sedimentary layers, the volcanic layers, which are deposited one over to the other, forming a sequence parallel to subparallel beds. So that such beds which are, we can say those are all conformable. They show the conformity. When conformable beds are formed during the continuous deposition or during the separate event. So close in time that the age difference between the younger and the older layers. Older layers and cannot be detected with the available methods. Yep. So that some contacts maybe we see in the contact between beds in conformable sequence are referred as a normal depositional contacts. And these contacts are usually planar or slightly irregular in form. Normal depositional contacts are distinctive because the properties like the color, composition, lithology, texture, and thickness of the layers which are involved. The deposition contact of the type are different from the normal depositional contact, which also occurs in different rocks. So the term we are calling that is as a unconformity. Yeah, it is an unconformity depositional contact between the two rock formation between the two ages. Between the different ages which are happening. Unconformity is represented with a break in the stratigraphic sequence, and that is the indicating the period of a time that are not represented in the stratigraphic columns by rock units. This break maybe it's due to the period non-deposition or the non-period during the its previously formed rock eroded. Hence, the unconformity is identified such as a surface that is non-deposition or erosion. Then that's layers which are separated. One it is starting from the single to the old stratas. Yeah, it is very common we see in surface erosions. Just we see here these pictures. A it is actually segmented rocks above and below, and B it is indicating. B it is indicating here we can able to see the small a and the small b, also the small a and the small b. This is the unconformity formation between the two rocks, and we see the B sedimentary rocks below and the volcanic rocks above. Yes, here it is A and B. There is both are sedimentary rocks above the A and here between these compacts. And when you come into the C, the volcanic rocks both two sides of a volcanic rocks which are having C. It's the A contact. It's showing here A to B. Above and below the both are volcanic rocks were present. formation. And D, here in a D, it is a plutonic rock below, and above it has a sedimentary formation. And plutonic rocks below and above rocks above in E formation we see here. Then the evolution of time gap, it is represented by the unconformity is not easy. It's not easy. For example, if you say the tertiary beds, the rest of Devonian beds, it is a possible. It is possible that deposition originally continued through the Carboniferous time. The Carboniferous beds having seen subsequently eroded away, leaving on the Devonian beds. Again, it is possible that deposition may occur in any time between these Carboniferous and Tertiary. When you see the Jurassic, in the Jurassic and its erosion and maybe it's removed these rocks before the Tertiary rocks and they were deposited. And unconfirmed develops through the several stages. First, the older rocks are formed. These later uplifted, sometimes deformed and subjected to the subaerial erosion. And finally, we see the younger beds or deposits. The unconformities may be yeah, and unconformities developed through several stages. First, older rocks are formed, and these are left uplifted, and sometimes more deformed and subjected to subterial erosion. And finally, the younger beds are deposited. Unconformities may be present between the rocks and the same origin of the rocks. Yeah, different origins, segmented rocks and volcanic igneous, plutonic igneous, plutonic and igneous rocks, which are metamorphic, maybe involved. So, type of unconformities in a different there are there are four types of unconformities types we see depending on their formation of the rocks and which rocks were involved and which are having their relationships and those in unconformities are one it is angular unconformity, second one is unconformity, third one is a local unconformity, fourth one is a non-unconformity. Angular unconformity is angular unconformity is the surface of erosion that separates the strata which are not parallel. The two groups are strata show differences in both strike and dip. The older strata usually it's a tilted fold and subsequently which are eroded before the overlying strata was deposited. The younger strata are essentially parallel to the unconformity. Some angular unconformities represented many millions of years as per geological time, we see. In disconformity, the strata on opposite sides of the unconformity which are parallel. In a disconformity covers a large area and represents a considerable interval of the time. A depositional break or less magnitude than disconformity is best. The densest or the smallest breaks when recognizable in the deposition of the sedimentary soils. And when you come into the local unconformity, the local unconformity is it's also one type of disconformity, but it implies the name which implies it is a distinctive local extent in the local formations. And it is time involved, it's very short here. During the deposition of the continental segments, such gravels sands, and the clays. The stream moves its back and forth thrust uh, across the basin of sedimentation. During the flood time, the streams cause out scores of channels, and these channels, which may be the each wide and deep, as the flood recedes, the channels filled up again with sediment. A nonconformity is an unconformity that separates younger sedimentary or volcanic from older crystalline rocks. The great unconformity is known as a Antioparcan unconformity. So that here, the Eparchan unconformity, it is located between the metamorphic or interior igneous rock, or sometimes maybe it is the core. So that we are calling this is as a Eparchan unconformity, a non-unconformity. This unconformity is separates Archean crystalline from the overlying the younger segmental formation. This is and then another more or less the common type of unconformity is also recognized. It's a phase of erosion. It may sometimes be without a very thick residual soil, which is formed as a grade wise, which is the underlying of the bedrock. And the younger sediments deposited above this erosion surface, maybe it is not visible. So such contact it is called as a blended unconformity. It is called as a blended unconformity. How we can recognize phase unconformity? Yeah, unconformities are sometimes confused with the faults and igneous content. Yeah, the following steps we need to take to recognize the unconformity. Suppose if you see the outcrops characteristics and presence of the basal conglomerate, must and sugar. And then second one it is aerial mapping. We should have to do the aerial mapping and sharp contrast in the degree of inturation and distinct differences in the grade of the metamorphism. And differences in the intensity point of the folding. And one more, it is a relation to protonic form. Fossil formation also. As per fossil formation also, these all explanations are given here. And second one it is joints. Its joints are which are related very which are formed and relatively on a smooth fractures which may found in rocks. These are formed in a brittle behavior of the rocks, which are subjected to shearing and tension forces. The word joint was first it was used by the coal miners of the Britannian smooth straight cracks. Those are separating the blocks of the rock, which appeared to have been joined as a brick work. The joints being the right angles to betting planes. Most joints you may see in the planes, but few curved surfaces. Many of the joints are initially tied to features, and due to the weather, they become enlarged where they form on open figures, and they should have to be visible to displacement travel into the giant surface. So that here the displacement it is called as a fault. So if it is a major displacement, then automatically we can say that it's a fault. There may sometimes a slight movement and right angles to the joint and process and this is produces open pressure. Joints may extend from few meters sometimes up to it is we see up to that is hundreds of meters. They may spaced. They may be spaced very closely a centimeter or even less apart. So sometimes maybe the distance it is having a few meters. The fractures which are very small and we can see and we observe only under the microscopic. It is called as micro joints. Yeah, these are joints which penetrate several strata and persist for a long distance, which are called as the master giants also. So here the master giants we see in aerial photographs and can sometimes to be traced for a distance of several kilometers. Giants which are usually occur as a group of factors with a more or less regular spacing in a given rock type. Yeah, in a group of joints, common, its origin is called as a giant set. The joint, which are usually more or less parallel to each other, they may be one or more sets of joints in a rock body, two or more joint sets of any group of joints with the characteristics of the system. Yeah, yeah. See these characteristics of the giant systems that depend on their sizes and the spacing and the arrangement orientations of the joints. As showing the variation, some degrees across the catchment, contacts between the rock formations, depending on their different ecology. Yes, you see here the attitude of joints. The joints may be see here, it's indicating the A, B, C, D, F. It is a vertical joints, and the striking it is known as a E and F. And E and F, and it's the trending. It's showing the east and the west. AP it is indicating east and west, and CD it is also indicating the east and west. Suppose if you see this B, D, and E, yeah, it's a vertical joints. The direction it is north and the south. So here the strike, of course, the strike if it is a joint is the direction of the line with the intersection of the joint plane with the horizontal plane. In the dip it is a angle between the horizontal plane measured in the vertical plane. Yeah, GHIJ, joint striking, not south dipping. It's almost 50 degrees angle. It's a bend. So the strike direction is also very important here. And we come into the classification of the joints. Your joints may be classified based on their geometry and their genesis. The geometrical classification is of a descriptive nature and can be easily applied. The genetic classification, on other hand, involves the interpretation of forces responsible for giants and therefore not readily to accept. A geometrical classification, if you see into the geometric classification, in a geometrical classification, the joints which are classified on the basis of their attitude, the relationship to the attitude of the bedding planes, some similar structure to the rocks. And there are four types of joints we recognize. Those are the strike joints, dip joints, oblique joints, or we are calling there is a parallel joints. And we see some bedding joints also. Yeah, in the strike joints, it's we see that is A, B, C, D, and G, H, I. A, B, C, D, it is a dip joints, and it's a thick black layer in a bed. And A, B, C, D, G, H, I, it is a dip joints which are showing the dip joint G, H, I. This it's G, H, and I. It's coming like this. G, H, I. It is a dip joints, please. And BDEF. BDEF, it's B, D, and E, F. Where it's M, M, and O. It is a strike giants tools. J, K, and L. It's a bedding joints on the same formation. Again, we see the P, Q, R also. It's a P, Q, R. This PQR and STU is maybe T. Cannot able to identify T here, but you here. STU, these diagonal joints. Your strike joints are those strike the parallel to essentially the parallel to the strike of a bedding of a sedimentary rock, and we see the viscosity of a cyst, the genetic gneissic structure of gneisses. The joints are those that are strike parallel or essentially parallel to the direction in which the bedding is viscosity of the gneisses structure. Oblique or diagonal joints are those whose strike direction lies between strike and the dip direction, and it is associated with the rock. Bedding joints are parallel to the beds. Next one is genetic classification. We see here genetic classification. It's A, B, C, and G. The vertical, it's a dip joint, and extension of a joint, this one. E, F, G, H, it's a E, F, Z, H, it's a vertical strike. It's a release to the joint. Then here, based on this classification, it's a genetic, depending on their genesis, we will classify. The majority of the joints for tectonic origins, some of them produced by the residual stress, and some of the produced due to some events occurred with long fracturing. Some by the contraction due to the shrinkage because of the cooling, and some by the surface movement, such rock slides as a landslides. And tension factors result from the stresses that it's can pull to the rock apart. Wide shear fracture result from stresses that tend to slide one part of a rock past adjacent rock. Yeah, in the folded regions, many joints are found to be systematically disposed about the folds, and these are supposed to have resulted from the same compressive forces which have produced the access folds. The access folds are called the extension of joints. They are formed perpendicular to the axis of the folds. Some joints are produced to expansion about the release of load. These called relief joints. Here, some joints were developed adjacent to the major faults. So such type of faults we are calling that is a feeder fault joints. These occur in the immediate vicinity of the fault plane, and in respect to the fault acute and pointing in the direction of a relative movement of the block and containing the fractures. They are tension joints. We are calling those the tension joints. Yeah, some important joints. Study of these importance of joints. It's many geological and other investigation in body of rocks with construction purposes. Greatly influenced by these joints, and the study of orientation of the concentration joints is very essential for engineering projects. And horizontal joints, which are closely spaced and which are unfavorable for tunneling. The large joint dipping towards public passages or sites for potential landslides. Those occurrence of the groundwater in hard rocks like the granite, and it's controlled by the joints. Well drilled into the highly jointed granites are the more productive than those drilled into the less jointed into the granites. Yeah, we come to the poles, which the pole, yeah, in many of the rocks, we were once approximately the planets of places that have been deformed to produce a curve. Yeah, coming to the to discussing about the poles. Actually, in many of the rocks, when we see this is a formations of a different structures, and some plane surfaces which are having a deform, which are produced with the curved structure, and non-planar surfaces. So such type of surfaces which are having curvature nature. So these curvature nature of our structures we are calling as a poles. And these poles are we in general terms we calling that is the wavy undulations. So it's looking like that the wavy undulation structure in different rock formations. So such type of a wavy undulation formations we call as a pole formations. Yeah, all of these edge surfaces which are having poles, and visually these most of the obvious manifestations we will see in a tactile formation of the rocks. Sometimes maybe these poles which are having the displayed the best in the stratified formations, like we may see in sedimentary formations, or sometimes may seen particularly in igneous formations by the lava flow movements, or sometimes maybe we see in metamorphosed forms also. Yeah, actually we consider these faults are seen particularly in primary core structures in the metamorphic and plutonic rocks. And faults which are formed under the different conditions, maybe due to having the stress in the hydrostatic pressure, both and the pressure and the temperature. Yeah, this is best evidence when we see in the same formations we see in different rock formations as those structures are defined as faults. Yes, we know faults are vary in different size and their shape, and again the arrangement of in a orientation. They occur in every conceivable configuration. Some are upright and some are not. So these layers we can see the nearby the neat arrangement of unconformity areas and thick other areas and other irregular formations. So that these sometimes it's repeated like a wave formations. Some poles are a few kilometers across, others are a few meters, and say are a centimeter, or even fractions of a centimeters in a way. So regional poles are hundreds of kilometers wide, and we can see the best only through the such type of farmers by with using of the satellite imageries. It's also having some thoughts. The sites of poles, sites of poles are called limbs. Every limb it is shared by the two adjacent poles. Yes, must. And then we may find out the hinge. The hinge of a pole it is a line and it has a maximum curvature nature and it is near to the folded surface. Each fold surface it has a separate hinge. Those hinges are maybe horizontal, or sometimes maybe it is inclined or vertical also. The axial plane it is a surface and it's connecting with all the hinges. It is maybe a plane surface or maybe it is a curvature surface or whatever maybe it is. So those we may find out. And again, it is a divides the fold more or less symmetrical. In some profiles, the axial plane it is represented by some line, and the attitude of an axial plane maybe it is horizontal or maybe it is inclined or sometimes maybe it is a vertical also. So that's the attitude of an axial plane. It is defined as according to the strike and the dip. Suppose if it is just in the case of a betting plane, again then we see the axis of the flow. So here the axis of a fold, it is a line, it's a parallel to the hinges. It is formed by the intersection of an axial plane and folded surface. Some use the term axis as a synonymous with hinge formation. So here we may find out here two types of two types of words. One it is a crest and second one it is a trough. The crest it is a line, it is a connecting the highest point and the same bed formation and it has an infinite number of sections and each bed has a separate crest. The plane or surface formed in all the crests is called the crested plane. So that's the crested plane we see on a top side. Then second one, it is the lowest points. The lowest points which are arranged parallel to each other, and the number of across sections, the point it is called as a trough. The plane is containing a trough line. It is called as a trough plane. Okay, I'm stopping here. We'll see in next class.